Hello everyone, this is Lab 6, Rotational Inertia of Disk and Ring. Our objective in this lab is to find the experimental rotational inertia of a disk and the experimental value of a ring. And then we are going to compare these values to the calculated ones. So you are going to see that your report is divided into two parts. In the first part, you are going to calculate the rotational inertia using the known expression or formula. Then based on the procedure, so based on the experimental procedure, you will see that from a set of data, we'll be able to calculate an experimental value of the rotational inertia. So this value will be compared to the calculated one. Now, before talking about the experimental procedure, let's have like a briefing or an introductory to the physics behind this lab. So an introductory to rotational inertia. As we all know, inertia is defined as the resistance of an object to change its state of motion. So it depends on the mass. The bigger the mass, the bigger the inertia. While rotational inertia is had the same or similar definition. But here we are dealing with rotational or circular motion. So it's the resistance of an object to to change its state of rotation. It depends not only on the mass of the object, but also on the distribution of the mass. The further the mass is from the axis of rotation, the more rotational inertia. So basically, it's a property of any object which can be rotating. It's a scalar value which tells us how difficult it is to change the rotational velocity of an object around a given rotational axis, as you can see here. So rotational inertia is given by the symbol I, and for a single body of mass m, like it's a general formula of the rotational inertia, as you know, the expression depends on the distribution of m on the shape of the body. So rotating a mass m at a radius r from a center or a axis of rotation. Now the rotational inertia is given by the product of m and r squared. So to understand or to be able to study the motion of a rotating object, we need to understand that we don't have regular or linear motion here. So the known variables, the variables that we have already studied in, let's say, in the 5 or 4 first labs, they are not the same. We know that to describe a motion, we usually use the displacement, the acceleration, and the velocity. So here you need to know that you have the same approach, but we are going to see that the variables, they are not linear anymore. So for circular motion, we have different variables, but these variables are related to the linear ones. So let's take a linear motion. We know that for a linear motion, the object is moving from one point to another point through a straight line. And we can define the displacement d in meters, the velocity v, and the acceleration a to describe the motion. Now, also in circular motion, we have what we call angular variables. Also, we have the displacement, but here we have the angular displacement theta, the angular velocity omega, and the angular acceleration alpha. Theta is the angular displacement, and it's equal to the length of the arc. So the travel distance L over the radius of the circle, so our trajectory. Omega is the angular velocity, which is also can also find a relationship between the linear and the angular velocity, and of course they will be related using the radius. And alpha is the angular acceleration. Now, if we take every point in a rotating body has an angular velocity omega and also a linear velocity omega. We know that the velocity is tangent to the path. They are related by v equals r omega. This shows that the object further from the axis of rotation will make or will move faster. So if we take, for example, here this gray road rotating around a circle counterclockwise in the direction of it's rotating in this direction. So here it's the positive direction of the motion. All the points of the road, they have the same rotational speed, but the black point in the middle here, this one, it has a less linear speed than the blue, or here it's than the yellow point attached to the blue path. If we are considering that we have a constant angular speed, so if we increase r, so if we increase the distance between the object and the rotational axis, the linear acceleration, the linear velocity will increase. Now, regarding the acceleration, it's defined as the rate of change in velocity in the case of rotational motion if the angular velocity omega of a rotating object is variable, so it's changing. In this case, we have what we call we have an angular acceleration. You know that if the velocity normally in linear motion, if the velocity is not constant, we have acceleration. Now here you need to differentiate between two accelerations. The centripetal acceleration that we have already defined in lab 3 in the centripetal force lab, it's equals to v squared over r. So the centripetal acceleration is related to the linear velocity and to the radius. And we are not going to deal with this acceleration. Now, if we want to find the tangential acceleration, so if the acceleration tangent to the path, it's the derivative of v respective to time. It's r, we replace, we know that v, it's omega r. R is a constant, so it's the derivative of omega respective to time. The derivative of omega respective to time is the angular acceleration. So to convert from the tangential acceleration to the angular acceleration, we have a relationship A equals R alpha. Okay, so this acceleration is different from the centripetal acceleration. The centripetal acceleration is directed toward the center of the circle, while the tangential acceleration is tangent to the path. If omega is constant, in this case, the derivative is 0, and the acceleration, the tangential acceleration, is in this case 0. Now, to change a motion, we need to apply an external force. Let's define the torque tau, which is the rotational equivalence to the force. So the torque will cause an object to rotate with an angular acceleration. A torque is needed to rotate an object at rest or to change the rotational mode of an object. So when we are going to use tau, tau is used to change the state of the object. If the object is at rest, it will start rotating. If the object is already rotating, we are going to change the velocity of this rotation. So the torque due to a force F, so F is the applied force, and the torque due to this force F relative to a point O is defined by the vectorial product of R and F. What do we mean by R vector? R vector is the vector between the center and the point where we are applying the force F. F is simply the applied force. The magnitude of the torque, so as you can see, it's not a scalar product, it's a vectorial product. So that's why tau, it's a vector. The magnitude of the torque is given by the magnitude of r, so it's simply the radius times the magnitude of the applied force times sine theta, where theta is the angle here between F, the applied force, and the rod, for example, here. So to have a maximum value of the torque, sine theta must be equals to 1. So in this case, F should be perpendicular to R. What does it mean, F perpendicular to R? F is tangent to the path. So when we apply a tangential force to the path, in this case, we are going to obtain a maximum value of that torque. And the torque in this case, it's simply F times R. Now, how does the rotational inertia relate to Newton's second law? In fact, rotational inertia takes the place of the mass in the expression of Newton's second law. We know that the summation of the force acting on an object is equals to ma. So here what we are going to do, we are going to find a rotational expression. So instead of using the normal or the linear expression, are going to see that we can replace, because we already have a relationship between the torque and the force. We have a relationship between the mass and the inertia. We'll be able to like derive another expression. Let's consider again a mass m attached to a rod. Okay, so here the rod in gray, it's a massless rod, so we are not taking into consideration the mass of this rod. It's only the mass of this body m. Okay, in this case, Ft, the tangential force, is equals to m times at. So here we are considering that the other end is fixed to is fixed, so the system can rotate about the central fixed point, as you can see here. So one end is like free and the other end is fixed. Now let's start rotating the system by applying this tangential force Ft. From Newton's second law, we'll be able to obtain this expression by replacing F net and F net by Ft, A by At. So this can also be written. We know that we have a relationship between At and the angular acceleration. So we can simply replace At by R alpha. So Ft, it's equals to mR alpha. If we multiply both sides by R, we will obtain the expression of the torque tau. And also, as you know, the inertia is equals to mr squared. So here, tau is simply I alpha. So as you can see, this expression is similar to this one, but instead of having the force, we have the torque. Instead of having the mass, we have the inertia. And instead of having the linear acceleration, we have the angular acceleration. So tau is the equivalent of F, I is the equivalent of M, and alpha is the equivalent of A in our system or in our motion. Now, how do we relate this to our experimental work? So first, we need a rotational apparatus with a step pulley. We have a here. It's a frame base. We need also threads or strings to attach a mass. We need you will see in the video that you have a pulley with a photo gate, but it's not shown here. And we are going to study the rotation of a disk and a ring. So in this experiment, you will see in the video that we are using a disk and a ring. We are considering that we have a uniform mass. and we will apply a torque by adding a weight. So by using the hanging mass. So the theoretical expression of a disk for the rotational inertia of a disk is I equals 1 over 2 mr squared. For a ring, it's 1 over 2 m r1, where r1 is the inner radius, r1 squared, of course, plus r2 squared. R2 is the outer radius. So here I'm representing like a top view diagram of the disk or the ring with a hanging mass. So here you have the disk or the ring and the hanging mass, and also you have a side view. This is the representation of our experimental setup. So basically what we are going to do, we are going to wind the thread up, and then like we are going to by how can we like when the thread you need to rotate the platform, then we will let the rotating platform begin to turn, and in this case at the same time we will start recording. We are going to record a so here as you can see, whenever we will start by going by winding, so by turning clockwise, then we will release the platform. It will go down. Okay, so the hanging mass will move down. And at this time, we are going to record a VT graph using this photo gate. So the photo gate is similar to the motion sensor, but the photo gate will be added somewhere here to be able to detect this motion. This photo gate is studying the motion of the hanging mass. And as you know, the slope of a VT graph is the acceleration. So how could we get the rotational inertia of a system from this acceleration? We need again to use Newton's second law, to apply Newton's second law to our system. So here we follow the sign convention that counterclockwise torques are positive and the clockwise torques are negative. Okay, so we are considering that falling down is the positive direction. Let's consider the hanging mass M. It's attached to a thread. So we have here two applied forces, the weight of the mass and the tension of the thread. We have a disk here. It's horizontal. The string passed over a pulley, the one represented here in blue. As the hanging mass falls, the disk rotates counterclockwise. This rotation is due to the torque exerted by the tension force, which arises from the weight of the hanging mass. So, in other words, if we attach a mass, by attaching a mass, we have a weight. We have a thread, so a tension equals in the magnitude of it has a magnitude equals to the weight, but in opposite direction. So this tension is simply the applied torque. So due to this tension, we have this rotational motion. Now, if we apply Newton's second law, mg plus t equals to ma, we do the projection minus mg plus t equals minus mat. If we consider that falling down is the positive direction, in this case, mg minus t equals mat. So t it's equals mg minus mat. T is the applied force. So T it's simply it's Ft. Okay. So tau it's R times T. In this case, T it's tau over R. And also we know that tau, we have already proved that tau it's I times alpha. So T it's I alpha over R. Again, we replace t by its expression in in the red equation. So I alpha over r, it's equals to mg minus ma. Alpha, it's at over r. We replace alpha by at over r. In this case, because we need one variable, m, it's a known variables. Okay, so m, it will be given or it will be measured. G is the gravitational acceleration. At is recorded using the photo gate. Okay, r is the radius. Okay, so we need like one variable. We cannot have several unknown values. Okay, so our target is to find I. We can replace alpha by its expression. So in this case, we have one unknown value, which is I. So from this experiment, by measuring AT, so by using the VT graph to obtain AT, we'll be able to calculate the experimental value of the rotational inertia. So here we have the same expression for the disk and for the ring, whatever the shape of the object placed on the rotating platform, we have the same expression. So as you can see, AT will be recorded using Data Studio. So from AT, you will calculate I. So I here, it's an experimental value, but it's a calculated experimental value. So regarding the experimental part, as you can see, we have many variables. So we need to measure the radius of the step pulley. So this radius here. We need to measure the radius, the inner radius R1 for the ring and the outer radius R2. And the radius of the disk R, the mass of the ring and the mass of the disk and the mass of the hanging mass. So as you can see, you have a lot of physical variables in this lab, and all these variables were measured. You will see in the data sheet if it was measured using a analog or a digital device. Now, regarding the calculation part, for the calculation part, or for the, let's say, the theoretical expression, for the ring, you will use the expression, but you will use the measured value of the ring and the two values of R1 and R2 to calculate I. So also here, you need to find alpha I. So by applying the propagation error, how many variables do we have? We have M, R, and R. So if you want, consider that you have two R to be able to do the derivative. Okay, so you do the derivative of I respective to M times alpha M, the derivative of I respective to R1 times alpha R1, the derivative of I respective to R2 times alpha R2. Okay, same thing for the disk. Here the expression, we have a simple expression, it's 1 over 2 mr squared. Also, we need to find alpha I. And don't forget to round the error to one significant figure. After rounding the error to one significant figure, the inertia should be rounded to the same decimal place. Now, regarding the experimental calculation, we are studying the motion of a hanging mass. You will see that we'll be able to record a VT graph. So the slope of a VT graph is the acceleration, it's the tangential acceleration. And we have proved that we have a relationship between AT and I. So from AT, you'll be able to calculate I. After calculating I, okay, and here, as you can see, you will see in the report that we have a repeated experiment. So after finding several times the value of the slope, you will find the average, alpha T average, alpha A average plus, I'm sorry, A average plus alpha RMS. Then I will be calculated from AT, and alpha I, again, the propagation error. You have an error on M, you have an error on R, G is a constant, it's a given value. You don't have an error on G, so no need to do the derivative respective to G, and you have an error on AET. You do the calculation for the rotational inertia for a disk and for a disk and a ring. So as you can see, we cannot do the calculation, the experimental part, only for a ring, while in the calculation part, we have a ring alone and a disk alone. So what you are going to do, you are going to find from the rotational inertia for a disk and a ring, and the rotational inertia of a disk, the rotational inertia of a ring. So simply by doing I disk and ring minus I disk, you will obtain the rotational inertia of the ring alone. So that's it for this lab. So regarding the lab report, so here you need to add all the values, and don't forget to add the unit and to add the error. So the calculation, please here show your calculation. You need to calculate I of the disk with its error, I of the ring with its error. So here, the tangential acceleration, we have several values. You need to calculate the average value with its RMS error for both cases, the ring and a disk and disk alone. Then here for the table, you have the experimental value and the theoretical value. In the experimental value, we'll be able to find ring and disk alone. In the theoretical values, we'll be able to find disk alone, ring alone. So you need to calculate ring and disk theoretical and ring alone experimental. Comment on your possible sources of error. You need to list at least three sources of error. Give 4 examples of objects or devices that depend on rotational inertia function. So here you need to know your own small research part where you need to find an example where we are applying or where the motion depends on the rotational inertia. Okay, so don't only cite the object or the devices. You need like to explain briefly, only with a sentence, how what is the function of the rotational inertia on this device.